Anybody else? Yosef, I see your name down there. Tuan, you can come to the classroom, but you'll go on I will record your name and you go on the in-person midterm. Okay, I'm looking at Yosef. Where's your name here? And okay, I think I got, yeah. Nicholas, I don't know if you want to record these, but somebody may ask you about it. Any other names? Tell me who you are. You're all welcome. I'm glad to help out. Okay, I think I got him now. Okay. Okay, announcement is today is the SI meeting. I like those meetings, even though I'm not allowed to attend. I think it's 5:15. Later in a couple hours from now. And just so if you don't have it at your fingertips, the number is 886-115-811. And I ran out of space 34. And that's the Zoom number for the SI meeting. And his name is Johnson. That's his first name. Maybe I've said in the past, I've known him a little more than a year. More than 1 year. I think he's a good guy, and he does know this hardware very well. I don't have any direction over him. He reports to a different supervisor, and he picks his own topics to present to you. And if you want to ask him about programming, go for it. He knows what to do about it. Let's see, announcements. The programs you finish. There were several email questions. Why don't you grade them? Directing it to me. And the answer is, you should know the answer. The answer is, I used to. Grades for programs. I used to, but as class size grew, it became overwhelming that I couldn't keep up. It became a physical impossibility to grade them all. And do a decent job of grading. There's crap grading that's pretty much meaningless, but to do a decent job, I couldn't do it anymore. The class size grew during the epidemic. Before the epidemic, it was around 25, and then it grew to 30 and 35, and last spring it was 42 in some of these sections. Others were limited to 40. Now we have the fire department of Fullerton is limiting us to classroom size. It's still not satisfactory. I'm in a classroom with 48 seats in it right now. I can't grade them all. I can't. I'd like to give you good feedback, but it's, like I say, an impossibility. So if you send me your program, I don't give you a grade, but I tell you what's good and what's bad. So you can get feedback about your program. Completed program. In the list of things, I admit it's kind of a low priority item, but it goes on the queue, and I'll get to it when I can. Feedback. And you should do it probably at least once before the midterm. That's kind of recommended. once before midterm. In the 8th week. So we got time. You want to know what I'm looking for. How should I say? I've received, I think, 4 programs for the feedback purposes, and one had no programmer's name in it. The other had compiling errors that didn't work. One did work nicely, but kind of like junk stuff I got. So you want to send at least one so you can get some feedback. One was the script file was made for for Windows. It wasn't Bash. I couldn't run it. If you do that kind of stuff on a midterm, see, it just goes to 0. So you want to make sure that what you send me can run on a bare bones Linux. It's Linux on the metal, not Linux in any other stuff. It's got to go the first time. I grade on 5 levels of when I did grade, but this applies to your midterm. I grade on 5 levels. Junk level is called elementary school. It doesn't compile. Middle is called middle school. That's where someone turns it in and says, teacher, it works. but the programmer's name's not in it. So I call it high school grade if it works and the author put his name in it and the due date and the class name. I call it university level grade if it has a purpose statement and explains what the program will do and also what parts of the purpose have not been fulfilled, like its limitations. And I've called professional grade if it's worth submitting to a job interviewer when you're applying for a high-paying job. If you want an A in the course, you got to go professional. High school grade doesn't get you much. Might get you a C-. I don't know. Okay. So why are you taking these courses? Why are you, during a 5-year period, taking, I don't know, is it like 20 computer courses with if you count the supplementary courses in math and science? So many courses. Okay, courses.
Professor, could you move the page down a bit?
Let's see, did I miss? Yeah, I'm sorry, I did miss it.
Or you move the camera or tilt the camera up more, either way.
Let's see if I get I'm trying to get that right. Okay. You're right. I should watch my screen once in a while. I have the little corner where I can see it. Okay, we have this fundamental philosophical question. Why are you taking all these courses? Okay. What's a good answer? One of my friends is a CS major. Does that count for points, or is that on a multiple choice question, is that a bad answer? Okay. Tuan says he's not sure. You get an office job that can't be automated and is just bureaucracy. No, Nicholas can't answer for the students. He's already experienced. Those don't count. Okay. My dad is a programmer, and says I have to do it too. Do the same. Okay. Is that a good answer, class? Jesus, what's the real answer in this multiple choice question? Oh man, we got to get prepared for the midterm. I can't believe this. Okay, how about nobody knows why you even in this major. When applying for transfer to CSUF, I clicked on the wrong box for major. Is that you? Why did you come here? Why did you pick this major? You got to have something. You're going to automate the bureaucracy. Yeah, Juan says that's going to be his answer. You're going to automate and get rid of these incompetent clerks. Oh, Tuan just clicked the wrong box. He meant to hit on something else like cooking, but it was in the alphabet close to computing, and so he hit the wrong box. No, Nicholas is not a student. He's TA. So you're the rest of you who are in this major. Oh, Charlie says it's interesting. Hey, that's one I haven't heard in a long time. I've heard these other three. Interesting. Stuff. Yeah, I think you're right. Traversal of a binary search tree is the most interesting thing I do in a whole week. You know, when I got free time on Saturday night, I get out the data structure book and I figure out how to do a left descent down through a N tree or B tree. It is quite interesting. Okay, anybody have the right answer yet? Yeah, you gotta be kidding me. You took a high school course, showed some proficiency and decided to devote myself. That's getting pretty good. So he has proficiency. Why select a major where you have no proficiency? Proficiency. ICIENCY. Okay, I gotta get it in the middle of the page. I sometimes forget. That's a good answer. You already have the skill. Have skill. Okay. I got the camera back in the right place. Okay. All of the rest of you fit in any of these categories? Your dad told you you had to do this career. Your friend is over here in this major. Therefore, you didn't even think about it. You just say, click on the same box that the other guy clicked on. You got here by mistake. Nobody's gonna answer. You know, guys. No, Nicholas, you gotta not interfere with this. You're not an undergraduate. That's not fair.
Hey, somebody
Nicholas, you gotta not give them the answers. Okay.
somebody posted at the same time I pressed enter. I'm surprised nobody said money.
I know. Wait, you're not part of the student body. You're a teacher. You're okay. Class. Okay. The game is screwed up. Okay. You're here because you want some money. Okay. And most people won't say that. I've done it over many semesters, and nobody wants to say, "Yeah, I want to get a job where I can get a nice, comfortable, big salary." Okay, now, so what do you have to do to get the salary? Okay. You pass all the, take all the classes and you pass, you walk over to Facebook Incorporated and you say, I'm here ready to work for you. Is that how it works? Joseph wants to make robots, choose something you're passionate about. Hey, that is important to have a passion for what you're doing. It's the greatest ingredient for success is that you really believe in what you're doing. I know money counts, but money just makes you happy. The passion makes you want to do it. And so you enjoy doing it. Okay, so to get to the big salary, there's a final exam.
Professor, can you tilt the camera?
Let's see, I think,
Can you like rotate the like arm forwards to have it point farther up the table? Or
the piece at the top doesn't turn. It
Okay.
either leans forward or it leans back. So maybe this
nerds.
can
Oh,
help.
they're kind of work. Yeah, you can see where the camera is. You can have more desk to write on.
Yes, I would like that. I'm trying. See if I can. We'll get there. We'll get there. Okay, see how this fits. Now, this is the base of a light. It's called a dog camera or something. That's the base of it. And the camera is facing straight down on this white area. Final exam. Okay, when is the final, the real final? Because final means there's no more. When you finish a semester, you have some final exams, but then the next semester you got more. When does the final exam happen? Final. It means no more, essentially no more of these tests. Okay. The answer is, we're running out of time, so I gotta speed it up. The answer is during the second half of the job interview. It's commonly called the technical interview. Okay, so the first part of the interviews, some human resource clerk comes along and asks, what are your interests like? What are your hobbies? Where'd you go to school? What do you do when you're not thinking about work? All that social stuff. But then the person says, just a minute, we'll have our technical representative come in and interview you for the second half. And that's this one. That's a test. That's called the real final test. And if you pass well, they may. Well, if you don't pass really well, they'll say, thank you for being here. We'll call you when we need you. But if you pass with good grades, you know what they say? Mr. Nguyen, you know, we really like your style here. We like your qualifications. The most we can offer you is 120K to start here. Would you think about it for a day or two and let us know if you accept our employment offer? If you pass well, you get an offer. Okay. So how do you get that? That's your goal. Remember, here it is. It's money. That's your answer. It's not, I know it's really fun to be in the same profession your dad was in, and it's nice to be in the same profession your friend's in, but that doesn't count. The one that counts for the next 70 years of your life is the cash. Cash brings you happiness. You can get a lot of stuff if you have the cash. Just ask Jeff Bezos. He will tell you it's really nice living this way. Do like I do. Okay. So to get that offer on the table, whatever it's going to be, you have to pass here. This is the big final test. Okay. So how do you prepare for the big test? I don't mean the one at the end of the semester, the one that really determines your life. The big one. Okay. Oh no, they've got a problem. The big final, I have to tell you, class, it's closed notes. It's no web searching, no notebook, no laptop to check out stuff. The big final is one-to-one. You have to answer in real time as this tech guy asks you questions. That's tough. So you prepare for it. Prepare probably 5 years. You take all those classes in software engineering and security and networking and theoretical algorithms until your blood is turning purple. You just keep studying all that stuff, and it's all for one purpose. It's one day you're up here, okay? And if you did well on all your studies, then they say, they'll tell you before you leave, we have an offer for you. Will you accept it? That's what you want to hear after all these 5 years. Why is it 5 years and not 4 years? Ms. Matt Gabriel Fernandez, 120K is just what you should be shooting for. That's your starting salary, and you want to go up maybe 180 after 3 or 4 years. Is that okay? Are you complaining or something? Well, what do you got against money? Okay, so you prepare for 5 years. Unfortunately, class, you're screwed because you can't make it in 4 years. Classes are full. Just ask someone who's trying to register late. The average, it's statistically, I've seen the numbers, it's 5.5 years from the time you leave high school until you can walk away with your bachelor's degree if you go to Cal State Fullerton. But I think at Cal State Long Beach is just as bad. They have just as much impaction as we do. So it doesn't get any better elsewhere. You just can't get it's rare. I guess there's 2% of the population who can make it in 4 years, but 5 years in one semester is the average. I knew the person. There was one who was here for 20 years because he was pursuing a double major and he couldn't get the classes in both majors at the times he needed them. So it is worse, but that's what it takes. Do your best when registration time comes. All right, so how do you prepare for it? You can prepare now. During the technical interview, it is very common that they say, show me something that you've built. What you can do. Okay, so what do they mean by that? That means they want to see some program. That's your major. You're not electrical engineering. They don't want to see a device. They want to see a program. Show me something you build so we can judge your quality of your skill. Okay, so now during these years at Cal State Fullerton, you're developing your portfolio. That's a collection of projects that you've worked on. Now, of course, in your portfolio, you only put the really good ones. Projects that you worked on in software engineering class, that you had a passion about it and you really put your best heart's effort into it. Save those projects, make them look cosmetically nice, and save them in what you might call your collection We often call it the portfolio. That name comes from the art majors who make a portfolio of their drawings and their paintings, and they show it to advertising agencies saying, this is what I can do. You're doing the same thing. You're saving your class projects that are the good ones, and you're going to show it to them when this one sentence comes up. Show me what you've made, what kind of work you've been doing. Okay. I'm all favor. You make your portfolio because you can beat the competition that doesn't have a portfolio. In this major, we save it online. It's not a physical thing like art majors have. So you save these projects in the cloud. GitHub is probably the most commonly one used. But it doesn't have to be that. That's not important. You save it in the cloud, and when the technical interviewer says, show me what you can do, you say, yes, sir, I have this URL printed on my business card, and hand him the card, and there'll be a link to some place where he can check your work. What kind of work is he going to find? What work? That means projects. Yosef is going to take more than 120 units. You max out at 120K for the entry job. That's after 120 units. You can't get 121K by taking 121 units. What work you do? Okay, I'll tell you the answer. It's I told you there's elementary school grade, middle grade, high school, university grade, and professional grade. It's your professional grade software. Put that in your portfolio, and you have a leg ahead of all the competition for the 120K. Okay, got it. Let's go on. Any questions? Any questions? Okay, let's see. I made a lot of notes. Let's see, where's page 1 of the notes? You still with us? Okay. In the coming days, when I emphasize professional grade software, you should have in your mind an idea of what I'm speaking about. I'm speaking about something so good that you wouldn't mind sharing it with somebody who's has all the cash that you want in your pocket. That representative of your corporation where you're applying is speaking for the corporation, and you're trying to get him to agree to send you $10,000 a month at starting rate. Okay. That's the grade of software we're aiming for. I hope you send me really nice ones so I can give you good feedback on. Chapter 1, class. At SI meeting, you'll do a lot of programming. He's an expert at all kinds of programming. All right, now, chapter 1 says students should know the difference between CISC and RISC. Okay, what if that's the interview question? Mr. Johnson, would you please explain to me the difference between a RISC processor and a CISC processor? And you want to jump right in and give the answer. Okay, so CISC, complex instruction set computer, or one of the computing. I'm not sure if it's computer or computing, but it doesn't matter. CISC. And so this one is reduced set instruction. Set computing. Okay, now it's kind of relative where the boundary between one is and the other is. The reduced means the number of instructions in the assembly language that goes with that processor is a small number. You follow that? It's, what is a small number?
Somebody's asking you to tilt the camera just a little bit downward.
Let me see. Does this?
No, not tilt it so, or they can't see the bottom of the page.
The bottom, about here. Okay.
Yes.
Okay, I saw it on my screen. It finally
You
popped
you
up.
good, Jesus?
Okay.
Thank you.
Is multi-threading possible on CISC? Yes, yes. In fact, that's, you're going to hear in 1 minute. You own a CISC. Okay, so there, it's a relative distance between the number of instructions in the assembly language that goes with a RISC machine and the assembly language that goes with a CISC machine. Relative numbers, it's hard to say, but less than 100, number of instructions, less than 100 is surely probably RISC. In fact, I think MIPS was less than 70 or even smaller than 100. If it's above that, you start to get in the territory of a RISC machine. I said that wrong, CISC machine. CISC means definitely greater than 100. In fact, Intel x86 has how many instructions? 709 as of last year, and it's probably still growing a few every month. When I last looked, late 2020 or early 2021, this many instructions. That's CISC, that's really complex. We own CISC computers, your laptop, your tower, they're CISC machines. Whether it's AMD or Intel, they're twins of each other. They are CISC computers. Okay? They're complex things. In this course, we'll probably learn less than 40 of these 709. However, there is good hope about 40 instructions. The good hope is with those 40, I found I can do 98% of all the programs I ever need to make. Only on rare occasions do I actually have to look for a Google search for something that I have not heard of before. There are many, but with these 40, you can make most of the programs that you'll ever need to make in this course or even after this course. Okay. Let's see. After that comes, why do we learn ASM? This is, I think we're almost, this is the end of chapter 1. Why learn assembly? Yeah. And I get asked this by email before the semester even starts. But let's give a few answers that the author says. The author says, by learning assembly, you're indirectly learning machine architecture. We'll see. That's kind of true. You learn parts of your computer by learning assembly. He also says you learn the tool chain. Let's make sure this is showing up on the screen. I think it is. Chain. The tool chain, I don't hear that term commonly, but he uses it. It's the collection of software things, software products that help you develop a program. So, like text editor, like NASM, an assembler. Like a compiler. Like a linker. And there's one guy we don't deal with very directly. There's a loader that brings your software from, say, storage on hard drive into memory and sets the first instruction to execute. Linker, loader, and how about one more? Debugger. Let's see, there may be others, but that's the key set that our author talks about. That set of tools is what the software developer uses to bring a idea into an application product and make it usable by the customer. That's the tool chain. Let's go finish that thought. He says, why learn assembly? Better, he says, it improves your skill for developing algorithms. Skill. Developing algorithms. Okay, that's kind of true. When you're developing an algorithm, you're thinking about where is this going to be executed? Is it in SSE or is it in general purpose registers? When you're writing a C++, you don't think in those terms. But after becoming knowledgeable in assembly, you start thinking that way. And that's a good thing. It says you'll come to understand the function call. Function call. When one function calls another, a whole lot of stuff happens internally. And assembly can look at those things happening. But at a normal language, C++, you never think of that inside what's happening inside the function call. And I just, on my handwritten notes, it just says the textbook shows a few other reasons to learn assembly, but I didn't write them down. Other reasons, others. Okay, on page 5, he gives some links to, oh, wow, you don't want to do this. There's links to the Intel developer manual to developer manual. You can download it. It's a free download. It's a set of 3 volumes. It's a fat 1,000-page ebook, in each case about assembly. Maybe you should postpone developing that because it's really quite frightening. So, but the link is there if you ever wanted to look. Page 6, the author says that he prefers YASM. Whereas I've told all of you to go use NASM. What are those? Those are assemblers that assemble source files into object files. I've looked at this one day and my opinion was that it looks like a close cousin to NASM. And I never went back to it. So his programs are tested under this one, not NASM. It doesn't make much difference to us. He has links to debugger information, page 6. That's there. We're at the end of this chapter. Links to GDB. And he teaches in chapter 6. In chapter 6, he teaches GDB with some extra burden that I don't like. GDB is in this chapter, and then it's burdened by another software product, DDD. That's kind of a front, it's a front GUI for users who don't conceive of assembly type stuff. This is a GUI that acts on this one. So we're beyond that. We're going to toss this out and never study it. But if you do read chapter 6, you sort of pass over the paragraphs that deal with DDD. So you have the word, official word, omit DDD. Okay. I got to get through this material. Let's see what we have after this. I'm teaching the book. If you missed any notes here, you left the room for 5 minutes. It's in your textbook, chapter 2. What we want to define is von Neumann. That was an individual who's now dead and was a scientist in the 1943 to 53 period. He was quite active and then died later. Okay, so in 1945, there were 3 computers in the world. Strangely enough, I don't know how the University of Pennsylvania got one of them, but they did. And the US Weather Bureau, whatever it's called, had one, and the Defense Department, the War Department at that time had one. So Mr. von Neumann was commissioned to go investigate all 3 computers and report on them. Because it was just all rumor stuff. There's only 3 in the world. And there's all rumor stuff. What do computers do? So he wrote a report, as I remember, around like 60, 70-page report on these 3 computers that existed at that time. And I'm going to summarize it now in the next 2 minutes. The report said that these 3 computers had 5 properties in common. 5 common pieces, components. And here they are. It had I/O peripherals. Okay, I/O is the monitor. That's an output device. The keyboard is an input device. The mouse is an input device. A scanner is an input device. A barcode reader is an input device. All those peripherals. That's one group. Okay, it said it had fast storage. What was he talking about? What we call today memory. Okay.
Would that be RAM?
Same thing. Yes, that's correct. I don't know if he knew the word memory or RAM. RAM is an acronym from
Random access memory, and what's it? ROM is read-only memory, which is something entirely different because you can't write to it.
right.
Slow memory is what you normally think of as, or what generally gets called memory or storage, I guess.
Yeah, we have number one, number two, number three. And here is solid state drives, hard disk drives. Do we have any other categories? Optical drives, if they still, if they're around. So that stuff is slow compared to memory. Memory is slow compared to the registers inside the microprocessor. 4 was the microprocessor itself. In his time, when this was written, they weren't very small. It wasn't micro, it was just a processor. And 5, there was some cabling or some circuitry to connect all these together. The name that stuck was, it was called a bus. Cables to connect everything. All right, well, so the report concluded that in the future, all computers would have these 5 common components. And that's quite a statement to say in 1945, but you know what, it came true. And all computers became known as von Neumann computers or von Neumann architecture. Machines. So any computer that has those 5 components is a von Neumann machine, has von Neumann architecture. And the prophecy became true. And to this day, the computers you carry, the computers I own, the computers you buy in the computer store or online, they're all von Neumann machines. Okay. So what's not a von Neumann machine? That's probably the quantum computer. You can't buy one. These are very expensive, tens of thousands of dollars. They only exist in labs like IBM Labs is actively researching these, but they're not von Neumanns. We, the public, they're too expensive, to put it in simple words. But after you get employed, man, you just go down and buy yourself a quantum computer, it doesn't matter. 70,000, that's no big deal then. All right, so next point, chapter 2 continued. Let's get through this. Sizes of data, names for size of data. Names for size of data. Okay, you ready for the list? Smallest addressable data is a byte, a word, a D word, D is for double. A quad word, Q is for quad. And an O word. O is for octal. O-C-T-A, I think that's how you spell it. Q is for quad word. D is for double. This is just word all by itself. And on this side of the equation, this means 1 byte. This means 2 bytes of data. This means 4 bytes of data. This means 8 bytes of data. And this is 16 bytes. Okay, so long ago, 40 years ago, computers were 16-bit machines. That's right here. And then came, 1990, came the 32-bit machines. And in 2005 appeared the first 64-bit machine. And that's where we are today. This computer doesn't exist yet. This is future. It will be known as a 128-bit machine. Okay. So we should give credit to, where was my mark? Here's where we are right now. And see, the information in registers are quad words. Every register, every general purpose register is of quad word size. In the SSE registers, each register has 2 quad words, but typically we're going to work with 1 quad word at a time. They exist independently. I can explain that. Yeah, I'm off the track then. An SSE register is XMM something. Am I in the center of the page? Okay. And if you drew a little diagram of it, it's like this. There's a quad word on this side, 64 bits, and there's one over here, bits. So you have 2 of them in 1 register. In this semester, all of our work is going to be done in what's called the low quad word. Okay, so is it a 64-bit register? Yeah, it still is. It just happens to be sitting with its neighbor under this name. How do you know that you're working with the low 64 bits? That's where the SD comes in. XMM 5, XMM 6. See, that SD says we're going to use the low 64 bits from here and the low 64 bits from here, add them together and get a low 64-bit answer and put the answer into here. Okay, so the extension to doing 2 adds at the same time is very simple. There's more stuff we need to learn that's more important. But if you wanted to add 2 at the same time, we're not going to use it. It's PD. So this doesn't show up in your homework, but you should know it for concept purposes. If you were to add 2 floats at the same time, you would set up XMM 6 to be 3.5 here and 7.2 over here, and then XMM 5, we'll make it say 4.1 and 3.3. And then you perform this kind of an addition, and what you get is XMM 5 becomes 6, 7. I'm adding the 2 right above me. And then on this side, there's a 5 and a 10. So you've performed 2 additions at the same time. So big deal. It's a very minor extension above adding, just ignoring this. We don't, with this instruction up here, notice we're just adding these 2, putting the answer here and discarding whatever's over here. We don't even look at it. All right, so how do we get here? We are in the era of 64-bit computing. It's a time era that started in 2005. That was the year the first one was ever released. And it's continuing now, but someday, we don't know when, they will release a 128-bit machines. I think we're 10 years away, but I don't know. I could be way off. Okay, let's see what else we have to do. I need to speed up. In C++, you should be aware of how to connect to the words we just used. Like if you declare a char, in C++, that is a byte. That's on the list of data type. If you declare a short, that's an integer, that's a word. If you declare an int, that's a D word, double word. If you declared a double, that's a quad word. And if you declared an address, that's also a quad word. All addresses are quad words, by the way. And that's an address to an integer, but the address itself is a quad word, even though the integer itself is a D word. Did everyone screenshot that? But you don't need to screenshot it. It's in your textbook. Okay, the page 9. Page 9. You know what the CPU contains? CPU, our processor, contains a whole bunch of stuff. They squeeze it all into a 1.5 inch square, only about 5 or 8 millimeters tall. Okay, it contains an ALU, arithmetic logical unit. Instructions are actually performed here in electricity, in circuitry. Instructions, I haven't looked up to see if there's any messages. Okay, nobody has a question. Instructions performed here, not in the registers. But in this ALU unit, it's separated from registers. There's a part that's called cache. Next class meeting, I'll have more to say about that. Cache is storage for data that's faster than memory. Data storage. You can transfer data in and out to cache, from a register to cache, faster than you can from a register to memory. So we attach with it the word of very fast. Yeah. You'll find in there, you know what these are, GPRs. Those are the registers that begin with the letter R. RAX, R8, RDI, etc. 16 of these guys. And what else do we find there? FPU, floating point unit. Okay. It by the way, is kind of fallen in disuse because it's superseded by the next one, SSE. But you'll find on the web lots of programs that access the floating point unit. It had 8 registers for floats. It's still there. It's not past tense. It's present time. 8 registers for float numbers. Yeah, it was superseded by SSE. SSE has 16 registers that are in 2 halves. I told you about that a moment ago. These are registers in SSE, a low half and a high half. There are 16 of these, 16 registers in 2 halves of 64 bits each half. Okay. And the last one is called AVX, Advanced Vector Extensions. And these are also 16 registers. Their names are quite similar. Not XMM, it's now YMM. YMM 0, YMM 1, YMM 15. And ooh. Yeah, so we don't study these because there's simply not time. And the author doesn't write about them. His book, he feels his book is too thick already, I think. So AVX is not covered in the textbook, and I don't test you on it, but you should know what it is. This is concept material. 16 registers. Their names are all with YMM. The difference is this is cut into quarters. So you have the low, well, the lowest 64, the low middle 64, the high middle 64, and the high end completely 64. So there's 64 bits in each of these. That's 256 bits in the register. Okay. Let me see if there's any questions. You got it all, everybody? Okay. Nice. Let me see if we had anything else. I think we're coming to our closing place. Okay, the author says, make sure everyone, oh yeah, let's go back to general registers. General. They have a way of dividing it by half, and then half of that, and half of that, and half of that. So most common one we use, RAX. I draw a box here. It has 64 bits in it, you know. And if you split it in half, they have a name for the ones on the right, but not on the left. So this over here is called EAX. And of course, there's 32 of them. And if you split that in half, they have a name for this group here. That's just called AX. And if you split that in half, there's a name for this group, which is AL. L is for low. Okay, yeah, and they do this for every register. I wrote down the R15 one. The book has the complete list for all 16 of them, how you split them up. You split this in the middle, then this piece over here is R15D. And you split that, then this piece here is R15W.
The camera has tilted upward again, or push the, oop,
I see it. There's a problem. So let's see if I can get it back.
there.
There. Okay. And you split that one more time, and then it is R15B. Don't memorize this, class. Those split off registers, we may never even use them this semester. Let me put a different color around it. Like, this is conceptual material that's not, you're not going to program this. So if I put a box around all this stuff, those are sub-registers within RAX. Same thing over here. It's rare. It might happen this semester one time, but it's unlikely. Don't memorize it. If you ever needed to know about them, go to page 9 and see the whole list for yourself. But you need to know where to find them. Okay. I'm going to end soon. I'm trying to get there. This is okay. So general purpose registers. GPRs. I keep talking about those. They're important. Means 64 bits. Okay. One hex digit equals 4 bits. Okay, so you do a division and you find out that one general purpose register 4 into 64 goes 16 times is 16 hex digits. Okay, and we write their contents in a hex notation. It would look like a sample. 0x is not part of the number. That's just a signal that says what follows is a hex number. So it could be anything. E048FF. And there's should have been on one line. That's a hex number. And for us humans, it's common to put a space between groups of 4. Okay. You will use that kind of stuff in future lectures and in future programs. You can put a constant into your program. You write it like that, don't leave any spaces, and it's good to go. It's good to move into, usually into a general register, but it could, from there, it could be moved into SSE registers. Okay, I think I mentioned it like in the first week of the semester, special registers that we don't program with are AX. Oh, is that special? RSP, RVP, and RIP, and R flag. I think there's an S on there like that. This is important. Marks the top of stack. We shouldn't put our own personal data in there. This one marks it's hard to describe, the back end of the region of memory that's actively in use by an executing function. That's a long description. It's okay, what is the back end? What's the front end? The back end is the high register, high address register. I can't say that. Okay. Here's a piece of memory. Here, the low addresses are down here. And the high addresses are up here. And a function is executing right now. That function is saving its values inside of here. 3.75, 4.6, 99. It's saving its values in here. That chunk of memory belongs to the function that's currently executing. The back end is here of that region, and there's a front end. The address of the number in the very back belongs to RBP. That's dark blue ink. That's the address of this one that's at the back end of this region that's owned by an executing function. That number will be stored in RBP. We'll run some tests in a future lecture and show you that that's actually the case. The address of the front end is RSP. I'll put it over here. As programmers, we can, but it's a bad idea to put our own data into RBP or RSP. Let's mark this. RBP. They're reserved, not reserved words, reserved registers. Okay. And so back here, this is the back end. And top of stack is the front end. Yeah. Front. Now, am I still in the camera range? I hope so. Okay. And this register, we don't touch it either. It holds the address of the next instruction that's going to move into the ALU. Not the one that's currently executing in the ALU, but the address of the instruction that comes next. Next instruction to execute. Okay, and I think this is the ending place on the notes. Yes, it is. Okay, our flags. Someone had a question?
Person is asking any specific reason why you draw the front of the stack at the bottom?
Yes, because we want low addresses low on the page. That's a common practice in assembly programming. Did I have that? Let's make it bigger. If I hold this up for me to view it, the low is down here and the high is up here on the page. So low addresses are here. And they get larger as you move up the page, up the ladder, and the high addresses are up here. That wouldn't make sense to have the high at the low. So the pushing and the popping occurs at the top. This is the logical top. So you push here and then you pop those away. And the high end is high addresses compared to everything else in the diagram. So we need a marker. Where is the last one of these? And that's RBP. And the top, say there were no pushes. This is the top rung, the top quad word. That would be RSP. If you had some other assembly books, architecture books, look at their diagrams. They're all in this nature. Now, I know it's upside down stack compared to the data structures course, but this is not data structure. This is architecture class. Okay, so where did I leave off? We all left off with flags. Is that in the center of the page? Flags is the last of these special registers. Flags holds temporary. Flags hold when an instruction executes, sometimes it has to record what it did. It's in flags, holds for a short period of time, holds results of not all instructions, but of some instructions. Okay, and I'm going to conclude with flags. I think I did it in this class where we had to, in one of your homework, you have to check incoming numbers to make sure that it's not a negative length of a side of a triangle. So you wanted to exclude negative numbers. And the way it was done is you need a register that holds 0, and then you compare the one in question against 0. So push keyword 0, and then move SD, we'll put it XMM10. And we're checking, for instance, make a comment here, XMM12 is being checked to see if it's negative. Okay. Are we out of time or something? Oh, hell, we are very close to out, being checked. there's a class who wants to get in here. That's the problem of in-person teaching. Okay, being checked. I'll stop. I promise you. UCOM ISD XMM 12 and XMM 10. Okay, so this is the 0. And this is the one in question. So UCOM ISD makes this comparison and says who's larger. The first one is larger than the second is larger than the first, or are they equal? It stores that answer in flags. So that's how come we have a flags register. It puts the answer in R flags. Certain bits are assigned to different parts of this answer, and those bits get turned on to a one value. Everybody else stays at 0. So I'm trying to explain, R flags is a register. We shouldn't go moving data into it. We should not say move R flag 17. You're going to mess up something. It's a storage place for instructions to put their outcome there for later use by another instruction. After this comparison, it puts an answer here, then we're going to use another instruction like JB that goes and checks that answer. So in a sense, the first instruction communicated with the second one via R flags. Okay. I talked as fast as I can go. We're really out of time, sorry, class. And that's good marketplace. That's where I ended with the other sections with the R flags. We'll continue conceptual material throughout this semester. This is not the end, it's just the start. And any questions for me? Okay, and so on. Joseph, did you get it all?
Yes, thank you,
Well,
Professor.
Okay, just remember, you're going to be tested on it at the technical interview.
And one last question from the chat. Can you push and pop from the RBP? And I told the person, can, yes, should, no.
Yeah, that's me.
No, the built-in instructions, push, pop. They only act on the top. They don't act on RBP. It's now you might cheat it and try to write some software that would insert something back there. In fact, you can, but push and pop only understand where RSP is. They relate to RSP. And they upgrade. When you do a push, it will subtract 8 from RSP automatically, 8 bytes in the push. And if you pop, it will add 8 bytes, add a number, the digit 8 to RSP's contents. Now you can program around that, and you can write some source programs that you want to change the value stored back here. Sure, I think almost everything is allowed. But as far as using the built-in push and pop instructions, no, they only understand RSP. They only know the front end of that region. Let's see, any other questions? Okay. He's got his thumb up. Okay, look for your 120,000, Joseph. Nice starting salary. Okay. But you got to be good at it. You got to convince those interviewers. You know what you're doing. Okay, just by the clock, everyone, I'm going to have to log off. I'm in a classroom where the actual people come in here at 4 o'clock.
I can answer some questions in the Discord if needed, but
Okay.
otherwise.
Everybody, you can go over to Discord and you can continue the conversation. Okay.